Morning, ladies and gentlemen. My talk is about pre-fermion theory of everything, along with talk about how viscosity separates general relativity and quantum mechanics. To me, physics, all the experimental results we have are all correct. I accept every single one of them, but I disagree with the interpretations of what they mean. And as Dr. Shapenko said this morning, I ask why. Why are these results, the standard model, what they are, and what comes on beyond the standard model? So my physics website is actually based on physics beyond the standard model, and that's why it's PBTSM. But basically, it's a very large subject, and I'm not going to give you lots of formulae. I'm just going to go through the outline, first of all, with some diagrams of what I think matter starts off as, and then do a bit of work on explaining why, and then conclusions, and if I've got time, I'll go on to the 6 basic principles. But to start off with, I want to really talk about what underlies everything, and what I think it is one particle and its antiparticle. That's it. There is nothing else. One particle and its antiparticle separate, and the separation takes the same amount of energy every time. And that separation energy is linked to the fine structure constant. That gives us the number that is the fine structure constant. And those particles, when they're separated, the particle, the antiparticle, they chase one way or the other way. And in separating, the separation gives a twist to the particles, they spin, and that gives them a charge as well. And the charge is 1/6 of the electron charge. So every time one of these zero mass black holes separates into a particle and antiparticle, you get a positive 1/6 electron charge and a negative 1/6 electron charge. Depending whether they go that way or that way depends which positive particle or negative particle has the positive charge or the negative charge. That's all there is. And what happens with these particles chasing is they actually catch onto other particles' tails. So each pair will catch onto another pair, and then form a loop. So you can think of what I'm thinking about as like loop quantum gravity, only with particles, or like string theory, only with particles instead of waves. And so my first diagram is quite simply, this is 3 pairs of these particles that are separated, and they're forming a loop. This is obviously not to scale. Particles are a lot smaller. They're basically the Planck mass size each. They are black holes, the most dense black holes possible. And basically they should be rotating. So that could be an electron, or it could be a quark, or it could be a neutrino. But that is all there is for our matter. If you've got anything other than 3 pairs, you've got dark matter. So if you have 2 pairs, or 4 pairs, or 5 pairs, 6 pairs, 7 pairs, that's all dark matter. Our matter is made of 3 pairs. That's where we get our threefold symmetry from. And what those pairs do is they stack. Sorry, the loops stack. So this, for instance, could be a boson. It could be a photon. It depends which way the particles are rotating and what they actually are. Okay, so they could be an electron and a positron rotating the same way, and they're a photon. All right, or they could be 2 quarks and form a boson. Further up the scale, you get a stack. A stack could be a neutron or a proton, for example. And if you've got a stack with an electron on the top, because of course, given that the size of the particles here are Planck mass size each, you can get electrons and neutrinos inside the nucleus. So if you've got an electron on the top of the stack and it gets hit by a neutrino coming in, it forms a proton. So weak force is just an incoming neutrino knocking an electron out, if it's got the right energy. And you've got loops everywhere, okay? The background to what we see is loops everywhere, as well as the original particles, which I'll come back to in a second. So this is what the background to the universe is. There is only one universe. There are no other ones, okay? And you have, initially, nothing. You've got your positive and your negative particles actually overlapping completely. So you don't see anything at all. But actually they vibrate and they rotate. And as they separate, you see them a bit more. But that is what the background is mostly made of. That's what I say the universe is. So there's no inflation of the universe. There's inflation of our expansion within the universe, but basically the sizes always stay the same. It's always the Planck mass size particles to start off with. And once more, as they come out, they unmerge, they become a pair. And those pairs chase, form loops. That's our fermions. Once more, this is a loop viewed from above. It's rotating. And these particle and antiparticle are chasing the one in front and being chased by the one behind. This is where negative mass comes in, which people won't like. But the positive mass particles I call positive bonds, and the negative mass particles negative particles. And you only see them inside the loop, because for every energy there is in the loop, there is an opposite energy as well. So this loop, no matter what the charge is on it, has no energy in total, but it still rotates. And that rotation is what we call the mass of the particle. So depending on the frequency, you might have that as an electron, or if it's got a faster frequency, it could be a muon, or it could be a tau. It's the size of the loop that tells you what the mass of the particle is. And here is a photon seen from the side, where you've got those original positive and negative particles overlapping. But they're chasing each other again, but this time they're chasing sideways as well as chasing around the loop. So what you actually have inside a photon is a force trying to chase these two particles along. And that chasing effect is affected by the background, all those other particles that haven't actually unmerged, as well as the other loops that are around, and that's viscosity. That's what I call the background viscosity to the universe, okay? So a photon is chasing as fast as it can do against the viscosity of the background. And depending on the viscosity of the background locally, that is how much mass there is, how much background, depends on how fast light speed is. But technically, it's always light speed because light speed can travel no faster. That is the fastest that photon can travel. So the velocity of light is not a constant. It's real, but it's not a constant. Next to a large black hole, for instance, it could be almost 0 meters per second, but it is still light speed for that photon. So what we have, where you look at a background universe with a photon traveling through it, is viscosity. And viscosity means loss of energy, redshift. So you have photons that have redshift as they travel through the universe. Okay? And it doesn't depend exactly on what frequency they have, so you don't see a dispersion when you're actually measuring the frequency of light coming from the same star or something, because they're basically all around the same size. The frequency change is not an awful lot. It's actually almost immeasurable when you look at it in terms of Planck frequencies. So it's the same redshift for almost all frequencies coming from the same star. So when you look out at the night sky and you see lots of redshift, part of that is redshift due to viscosity, and part of it may be due to the expansion of the universe. Because we don't know how much this is, we can't say how much expansion there actually is. I'm still trying to work out how to bootstrap a value for this. But then when you say, okay, let's look at the quantum side, and you look at a photon and you take apart an electron and a positron, and they're entangled, what you've got between them, I think, is a tunnel. And they travel along that tunnel, back and forwards, at the Planck frequency, but because there is no background in the tunnel, there is no maximum speed. So that's where you get the quantum effects. What's happening when you're actually measuring the superposition of two particles like that are entangled, what you're actually measuring is them going backwards and forwards. And when you measure one, the tunnel disappears, the other one gets stuck where it is. So that is how I see quantum mechanics and relativity being separated. You can never put them together because one is due to the background viscosity and the other one doesn't have any viscosity. So with a background viscosity, you get an arrow of time because everything is always losing energy as it moves. You can't do something and then undo it. You do something, it takes energy. You undo it, it takes energy. There is an arrow of time there. But when you've got the quantum side where you've got a tunnel where there is no background, you've got non-local action. So that basically is how I look at the overall picture. So this is a picture of how there are slightly different distances that the let's say positive and negative particles rotate as they go around, and that gives you the charge that you see, or the effect of the charge that you see, for instance, on an electron, and half of the effect you see, the anomalous magnetic moment, is due to the large mass or the large charge, and the other half is due to the small charge. So you've got electron charge and you've got muon Planck charge, and that's why you get G2. We're still working on the anomalous part. We're getting closer, but we haven't got the anomalous magnetic moment exactly at the moment. Let's say we're still working on that. And I did cheekily, before I started, sort of put on each of the desks in front of you sort of how the framework interacts. And it starts in the bottom left-hand corner. It's sort of trying to give you an overall picture of how it is. But now I'll start on giving you the explanation in a sort of formal way. So I say it's a hypothetical pre-fermion particle theory of everything. So it's particles, not talking about, the waves are actually the loops themselves. You look at it, you say, okay, it's a loop, it's got frequency, therefore it's a wave. It's symmetric. For every energy that you have from the mass side, there's an energy from the charge side. So every time you look at a particle, you have to look at what is the mass side doing, what is the charge side doing, and actually show how that arrives at what we see experimentally. And there are only two types of energy. Okay, there are only energies due to mass and energies due to charge. The strong force is an effect of the stacks. And let's get the stacks up. Stacks. It's an effect of the muons themselves. The particles are called muons. It's an effect of the muons themselves with other loops in the stack. And when you've got other stacks, it's across the stacks as well. And as I said earlier, the weak force is actually just one loop being replaced by another loop in a stack. In terms of matter and antimatter, when you've got a loop system, you need more degrees of freedom than people expect when looking at matter and antimatter. And actually, it turns out that the antiparticle of a +1/2 spin electron is a +1/2 spin positron. So a photon is actually a perfect pair. And so the only difference between matter and antimatter is charge. So when you've got a battery, you've got a matter-antimatter system. It's only the difference. It's matter and antimatter, positive charge, negative charge. Which one do you actually choose to be your matter? Your choice is positive charge or negative charge. I don't care which you choose. And that's why when you look out in the night sky and you look at other stars and galaxies, you will get the same energy gaps for photons, electrons, and all the rest, because whether it's matter or antimatter doesn't matter. Sorry to say that. And you also have, to go to the other end of the scale, why we have our expansion and our Big Bang is because there have been lots of other Big Bangs throughout the universe over unimaginable time, as far back as it goes. Because every time one of these pairs separates out and unmerges, it could set off a whole chain formation event. And that chain formation event is the start, possibly, of the Big Bang. And what happens is that the chains, as they go around, bang into each other, and if, as a result of that banging into each other, a loop expands sufficiently, what happens then is the energy that is lost because the frequency has been lowered by an awful lot is turned into motion away from that center. The question is, how large in terms of size, but small in terms of mass, do those loops become versus the energy that's pushing them away from their origin? Okay? If the loops are large enough, that is small enough mass, then they will continue to go out because there's a lot of energy pushing them out, and the energy of the loops is very small. So that's our successful Big Bang. But out there are failed Big Bangs, where the loops didn't expand enough. The masses were too large, the energy available to fund that expansion away was not sufficient. So they may have formed loops, but then contracted back onto one another to form black holes. And as they form black holes, the loops get broken. And what you get then is chain stars. You get lots of chains all breaking, reforming and all the rest, and only sending out symmetric photons that have just enough energy to escape. So dotted throughout the universe, and there is only one universe as I said, you've got failed big bangs, which are black holes. And you can actually see that if you find in the sky a source of redshift next to another source of redshift, which look as though they're conjoined in the same part of space. One has a redshift, the other one has a different redshift. To me, the one with the lower redshift is an original failed Big Bang, which is stationary. And we have the other part, which has a higher redshift, is actually moving away. It's part of our Big Bang. So it's a mix of steady state and Big Bang. That's what I think. It might be that the size of our electron sets the limit at which you have to have a successful Big Bang. Our electron is small enough that it could be that that's the reason why. And the reason why we get the masses we have, I think, is because the inflation that we had was along 3 dimensions. And if you look at three different values for inflation along those dimensions, I can actually come up with 11 of the 12 mass sizes for the fermions that we actually need. I can't come up with 12, but I can come up with 11. So to me, that's why we have 3 families, because we have 3 dimensions. There aren't any other dimensions. And as I said before, when you look at the electron, for example, why does it have 70 degrees of rotation? Well, it's got G as 2. It has G as 2 because it actually has not just the charge going around, it has also the muon large charge, Planck-sized charge going around, and that gives you the extra QBR that you need for the magnetic moment. So what that means is that physics is the same everywhere. Okay, there are no places where singularities exist, because the black holes have got chains in them, or loops if you want to have loops inside them, but those loops and those chains are made of muons, Planck particle and antiparticle that originally unmerge. Everywhere you have one of those, you can't have a singularity. These are the most dense particles possible. A black hole is like water compared to the density of the particles. So we're all made of the most dense possible black holes, and they're always in motion. So I like the idea of motion, your dynamical motion, but it's motion for a different reason. These loops are always going around. As I said, there is only one universe with only 2 energies. You also have to look at the fundamental units that we use as well, because at the moment the Planck units that we use have got the gravitational constant in there. You can actually get rid of the gravitational constant by changing the size of the Planck mass, changing the size of the Planck distance to incorporate the gravitational constant. Once you do that, you see that G actually has no units. It's a constant that is set by the size of the units that you use. So what that means is that inside the nucleus, the actions of mass and charge have the same size. G is just a constant you can get rid of. And what that means is that when you look at the properties of matter, you look at voltage, current, velocity, time, and so on, and you look at the fundamental units of those, they're all actually powers of the square root of the speed of light, or fine structure, the square root of the fine structure constant over 2 pi times the square root of light. Sorry, yes, times the square root of light. So, for example, mass is equal to the square root of light, the value of the Planck mass. If you use h as well, you've got h in there too, so the square root of hc. But that power is very powerful because length is to the power of -3, voltage is to the power of +6, power is +10, forces +8 and so on, and it actually shows how you can get rid of some of the units that exist at the moment in SI. So once you've done that, a lot of the numbers and formulae become very simple. Not all of them, but some of them. I think I said everything, actually. I mean, there are the 6 principles that I wanted to talk about, but so I've already sort of gone over some of them. But I mean, if you have any questions, I'd be happy to answer.
Now we can set some questions. Please, questions?
Would it be correct to say that you introduce a sort of vehicle which is viscous?
Which is?
Viscous.
A vehicle.
Because everything, as I could understand, life is rotation.
Yep.
Every particle.
There is viscosity everywhere, apart from in the tunnels between entangled particles.
So everything rotates somewhere in some medium, which is vacuum. So if this vacuum is viscous, must it be heated? What happens?
What happens is that your loops go slower,
you said about the losing of energy.
They transfer the energy to the background.
Yes, what background is heat all the time.
It's
by now it's
vibration.
there.
No. We've still got lots of energy to lose, because every time there is rotation, it means you haven't lost all the energy. So if I go back to, that's probably the best one. These get vibrated faster by the loops passing by. So they're taking energy away. So energy starts from here, through here, into the loops, and then goes back to here and here. So it's a circle. And if you look at the little postcard, I show that it's a circle. The energy does a circle.
Thank you. Next question. I have a question. You consider movement of the matter and antimatter particles without taking into account effect of annihilation. Am I right? Annihilation.
Annihilation. There is no annihilation. Everything is already here. Okay. So when, for instance, you've got uncertainty, and you say you bang something, you get a particle and antiparticle here. They were already there. Those loops already existed as y turns 0. So you have a particle and an antiparticle rotating in opposite directions. Photon rotates in the same direction. Xeron rotates in opposite directions. So when you hit one of those pairs, they separate out, and you can see a particle and antiparticle. There is no annihilation.
Thank you. Any questions?